Hey there! In this video, we're going to be talking about analog sensors. Specifically, we're going to be talking about the VR, or variable reluctance sensor. That one. VR. Our variable reluctor. This is a sensor that's used in a lot of different places. Like a wheel speed sensor, it's used in transmissions, it's used in engine performance. We use this sensor in a lot of places. It's a very simple sensor. It is essentially a coil of wire and a magnet, which we pass a toothed Ferris wheel past. When we do that, it produces an AC sine wave. This sensor requires no power to make it work. I'll draw up a quick diagram here. So first off, this sensor doesn't actually require any power, but it is an AC, or alternating current sensor. Okay. So because of that, it's going to switch evenly above and below a zero line as long as it's working properly. So the sensor itself is going to be a nice AC sine wave. And as the toothed ring passes by the sensor itself, it's going to alternate as the teeth come up and then drops into a valley. Now, the actual sensor, they can flip this depending on how you see if you flip the wires in it. But regardless, when you go past your teeth and your notches, one end is going to be a valley, one end is going to be a peak. The transition is everything in between. There's a small problem with those, though. The computer doesn't like this. A computer doesn't do analog. A computer does digital. So that's one of the downsides to this particular sensor is to use this. The sensor is cheap, but now they have to build an analog to digital converter inside the control module this is feeding to so it understands it. That control module is going to take this signal and it's going to turn it into a square wave internally. The computer understands, in fact, it's not even actually going to do this because it really doesn't see that. It's just going to see this as 1 or high, 0 or low. 1, 0, 1, 0, so on and so forth. Pretty straightforward, really. The best thing this sensor is for is giving us a speed. That's what it was originally used for. We got our speed from it. So the faster or the higher the frequency of the switches, that meant that the wheel was going past the sensor faster and it was picking up a greater speed or greater frequency. This sensor has a couple of important attributes. As we speed up, of course, that frequency comes closer together, but we're also going to find that at slow speeds, we make a little voltage, and as we start to speed up, that voltage is going to start to increase. Also, the same thing occurs with distance. The closer it is to its pickup wheel, the higher the voltage output from it. The further away, the lower the voltage output from it. These sensors will only output a voltage relevant to how close it is, how fast it's going, but the PCM only understands that as long as it's above about 250 to 300 millivolts. Below, so if this is below 250 to 300 millivolts, in that case, the ECM or the computer that's feeding to doesn't understand it anymore. Okay, one more thought on this before we take a look at it in action. Couple more. Okay, I'm going to give you a couple more thoughts. Something that you will find occasionally is the manufacturer will put out a voltage on one of the lines that sensor's on, Now that doesn't mean that all of a sudden that sensor starts to add 2.5 to its peak, but what happens instead is instead of switching across the 0 line, now that sensor switches up here across 2.5 volts. The computer does this for diagnostic purposes. It knows when it keys up that if that line is something other than 2.5 volts, that there's a problem in the circuit. If this line is higher than 2.5 volts, it knows that circuit is open because there's no ground on the other side. If that circuit is lower than 2.5 volts, it knows that circuit's shorted. There's a problem in it, or the sensor itself. So if you happen to see voltage on here, that's often normal, but what that really tells us is that's a diagnostic line for that circuit. And regardless of where we switch, the one other thing that's going to be a little different on this we can also use this sensor for position. If we want to use it for speed, then what we have to do is we look at how fast the frequency changes. But when we decide to use it for position as well as speed, what they'll do now is take that toothed wheel, which would normally, pardon my lousy artwork, partially be like that. They'll get rid of a tooth. So, what that's going to look like in the signal, in the pattern, or what the ECM sees, where that missing tooth is, you're going to have what we deem a signature in the pattern. We're going to have one spot where all of a sudden there's a difference. You know that's the missing tooth, and often a PCM will take that and use that to understand that, hey, I have a top dead center cylinder here, I'm coming up on top dead center of a cylinder, often number 1. Something is happening or about to happen, and this is how the computer's going to watch it. That's our basics. Next we're going to go out and I'm going to show you just a little bit in the lab about what this is actually going to look like on an oscilloscope. So we'll step out there in a minute and take a little better look at this. So here we have a Honda distributor that actually has 3 separate variable reluctors inside of it. You have a lower pickup all the way down there, it's got 4 teeth on it, a middle pickup, and then the top pickup. The lower pickup is our cam sensor, the middle is our crank essentially, and the top is considered our cylinder or TDC sensor. So we have 3 different variable reluctors. We have 3 sets of wires that come out for each one of those. Now to test that, we'll pick one of the sensors. We've got our meter here. We can do a resistance check. And as soon as we can get our clip to stay on here. Looks for right about 362 ohms. Okay. If we move to the next set, about 365 ohms, and the final set puts us at 364 ohms. Now I don't know what the exact spec for this is, but I can pretty much tell you that since all 3 are hitting about the same numbers, it's probably going to be pretty close. The other thing we can do, because this is an AC generating sensor, I set my meter on volts AC, and I can spin this, and you'll see we'll create some voltage. Here, I'll tell you what. Now let's see what we can do. Get these out of the view there. Two and a half. So we hit about 2.5 volts AC by spinning it. right here what we're looking at is a scope capture from a VR, or variable reluctor sensor. This sensor actually shows a signature in the pattern. You'll catch it right about in here. Let me grab the pen. So that right there, there's our signature in our pattern. You'll notice that we've repeated back over here. So that means that in this distance, we made one full revolution of our crankshaft on this particular engine when our signal repeats. Now, this isn't always the case. We can have more than one sync signal coming up on a sensor. And when we look at the Hall effect video, I'll probably give you an example of that. In this case, I know there's only one. So the distance between the two here is going to be our 360 degrees of crankshaft rotation, or one complete revolution. And each time the tooth wheel passes our pickup, we have our up and down movement, or it creates our sine wave here. So from here to here, we get our one revolution. And now the PCM can look at this and determine from the peak here to the peak here, and it's going to do a little quick math, and it can tell exactly where that crankshaft is at any place here. So, and I should add, this is actually a crankshaft position sensor on about a 2016 Toyota. So that PCM is going to figure out exactly where that crank is at any position in this. All right, next I'm going to use the same engine, and I'm going to show a little example where with the engine running, we're going to change the gap on the sensor with the pattern running, and you can see how a changing gap at a stable RPM actually will affect this pattern. So watch as I pull the sensor back, you'll see the amplitude of the signal drop. When I push the sensor back in, you'll see it rise back up. This really illustrates how important the gap between the sensor and the pickup wheel it's sensing happens to be. All right. So now that you've looked at some images, bottom line, the VR sensor can produce its own voltage, should have a resistance across it, may or may not have a diagnostic pulse. It's going to switch, and we have to watch its two biggest attributes: the frequency, which tells us how fast it's going, and the amplitude, which gives us an idea about how close or far we are away from our pickup wheel. Normally not a problem, but if you're cranking this an engine or something over, and it's not able to pick it up because it's too far away, then it becomes an issue. So you're going to look at amplitude, just to make sure the ECM can see it, and then we're looking at frequency, or how fast. And if it's in position sensor also, then we're going to need to look for our missing tooth in there and our signature in the pattern. What I really want you to take away from this is, I know we have some lessons where we delve deeper into how the sensor works and what the sensor really is. At the end of the day, it's an analog sensor. Is it producing a pattern? Does the pattern look right? If there's a signature, should there be, or do we have a broken tooth? Okay. Keep it simple works here as well. And even figuring out, do we have a VR or analog sensor or not? I'll give you one of the quick tips when it comes to EP, or transmissions for that matter. If it is a 2-wire sensor, it is most likely a variable reluctor. If it is a 3-wire sensor, then we're usually going to get a digital signal from it. Now, that's a different video. Doesn't matter if it's Hall effect, doesn't matter if it's optical, doesn't matter if it's an MR when we talk about EP stuff, it's going to be a digital signal. So right now, just worry about the VR sensor and remember the important stuff. All right, we'll catch you in the next video.